Hang on, huh? Hello, just give everyone a while to come in. Sonia, you're in, right? Hello? Okay. I'm just gonna go through that question first. Did anybody have any questions for me that I have not answered yet? Hang on, let me just open this up. There we go. Okay. So we got a couple of things going on here for this one. We've got stone A, right, falling through air at terminal velocity. So kind of like they did kind of inform us that it's at terminal velocity. Hang on, let me just draw this line. So through air at terminal velocity, right? So there's terminal velocity there already. Okay, so it's just telling us that okay, we have in a way you kind of like have to recall. So terminal velocity, what's that trigger then, right? So what's the big deal with terminal velocity? So terminal velocity, right? There's a stone, right? There's a stone there, and what are the forces, right? What are the forces acting on? What are the forces acting on the stone? So you have the weight, right? The mg of the stone, as well as the air resistance. So this is like drag. Okay, so if you fall through air, right? If you fall through air at terminal velocity, right? If you fall through air at terminal velocity here, right, like this, if you fall through air at terminal velocity, right, means that there's drag, there's air resistance, right? I mean, like I say again, I like to use the word drag because it's easy to write rather than writing the whole of like air resistance, but it is drag. Okay, so falling through air, right? Yeah, so drag is equal to weight. So we understand that so the two forces balance, right? Is terminal velocity. Terminal velocity means it's the right. What is the definition of terminal velocity? Again, it's the maximum speed attained, right? Attained in neglect. Just mute for a bit. Attained in presence, right, of air resistance. Okay, air resistance. Try to use iPads if you can. iPhones are really small, so it's like kind of like, yeah. But it's okay, don't worry about it, right? If you don't have any device available at this time. Hi Eden. Kinda need you to mute. Okay, I'm gonna have to mute you, sorry. Okay, right. But why is it maximum speed, right? So it has been falling for a while, right? The drag has been increasing, so the velocity of this ball has already reached this part here. Okay, so for the first sentence, stone A is already referring to this part where, right, this part where the velocity is already terminal, right? This terminal velocity. So you got to understand, terminal velocity sounds like it's the end, right? But terminal velocity really just means that it is the maximum velocity attained, right? So the velocity is constant. Okay, so that's what this means, right? Maximum speed attained in the presence of air resistance and all. Okay, so we got to ask ourselves, so what's the acceleration? So the acceleration, I mean, that's basically what the question wants, right? The question wants us to tell us what's the acceleration, what's the velocity. So it's already falling at air resistance. It's already falling at terminal velocity. It's not saying, oh, it's going to reach terminal velocity. It's already at terminal velocity. So what's the acceleration? The acceleration is 0, right? Acceleration is 0. It's not accelerating anymore. It's at maximum speed, but it's not accelerating anymore, right? So the acceleration has reached 0. Why has it reached 0? Right? In terms of forces, they didn't ask us why, right? If it's just I just want to know the answer, gosh, why do you have to explain so much, right? Right? If you just want the answer, sure, it's just 0, right? But why? Why is it 0? So the reason is why it's 0 is because you got to look at the two forces, drag and mg, right? You can say mg minus drag equals to 0, which means that resultant force is 0. So there's no resultant force, right? Resultant force is 0. So resultant force is 0. It's falling, but it's falling with like, maximum speed, right? Maximum constant speed. So for stone A, right, acceleration is 0, right? Velocity is constant. So that, at least, I mean, there's only one option for me, for stone A. There's only one option for me. Like, there's no other options. Like option A is not repeated anywhere else for stone A. Kind of like, if they had put down maybe 0 and constant for another one, then yeah, perhaps, but no, there isn't any. So technically speaking, A is just the answer. Of course, again, oh my gosh, Sam, why do you have to explain everything all over again, right? I just want to know the answer, right? Sure, and I'm going to explain to you why B is the why B is like that. So B, right? So if we look at B, right? B, it says B is falling through vacuum over the same distance, right? B is falling through vacuum over the same distance. In hang on, let me just, is this the bigger size? Hang on. Yeah, it is the bigger size already. Okay, sorry. So for B is falling with no air resistance. So B must be in a vacuum chamber, right? So it has to be in a vacuum chamber. Vacuum chamber. But you see, the problem is a lot of students like, oh, vacuum? Isn't space vacuum? So doesn't it mean that vacuum means no gravity? Nah, right? So you're basically just messing everything up, right? So a vacuum chamber is basically you create a little column, right? Like in the lab, and you suck out all the air. There's no air inside. There's gravity, right? Like it's on Earth. Like this is on the lab, right? In the lab on Earth, in school, right? It's just that the entire column inside has no air. So this object is now falling, and therefore the only force that acts on this object is the weight. There's no air resistance, right? Not like that one up there, right? So not like this one. This one is stone A. This one has drag. This one has no air resistance. This one is just weight. Okay, right? So in a way, as it falls, to fall, then you gotta ask yourself, so what's the resultant force for this guy? The resultant force F net equals to mg, right? Like it's not the same as the one with air resistance. The one with air resistance, mg minus drag, and then it's 0. The F net is 0. But for this one, the F net, the resultant force is not 0. It's mg. All right. What does it mean? It means that ma equals to mg. Right. It means ma equals to mg. What does that mean? It means that the acceleration is g. Right. So now the thing is that, oh wow, does it mean that this object will accelerate all the way as it's falling? That means it doesn't stop accelerating. It will accelerate and accelerate and accelerate and accelerate. The answer is yes, right? It will keep on accelerating. So if you were to draw a graph for this one here, you draw a graph for this one here, right? Velocity time graph. Then you will see that the graph, right? Then the graph of this one should go up, right? At a straight line, right? It will be a straight line. It will be like this, okay? It will be a straight line, right? Like this, and it's just going to be forever going up straight until it hits the ground now, So the area under this graph here will be like H. Okay. So for stone B, right? For stone B, what is the what is the options? I mean, we already know A's answer. You know what I mean? So acceleration is 10 meters per second squared. Oh, why is it 10 meters per second squared? Because that's G. That's what G is. G is, right, 10 meters per second squared. Right? That's what G is. Okay? So that's the answer for this one. Right? And the velocity is increasing. Yes, it is. In fact, it's increasing like that. Right? It's increasing like this. Right? Then, you know, if you come back to this one and say, oh, but isn't the velocity here increasing? Yes, it was increasing. But that's not what the question is asking for. The question is asking you, right? Or rather, the question is telling you stone A is already falling at terminal velocity. We are looking at the last part of stone A, right? So it's kind of like they're being very specific, right? The two sentences here, they're being very, very specific as to what they want you to compare. They want you to compare stone A at the last part, and they want you to compare stone B at the whole part, right? Okay. So therefore, for stone B, the velocity is increasing. It's accelerating, right? Now, final thoughts on this, because we've done air resistance quite often for the last 2 weeks already, right? It's a thing. I get it. It's an every year thing, right? Every time, right, when we come to this point where we start to talk about air resistance, it gets very muddled, right? So you either, you know, try to analyze it step by step the way I showed you the last time, right, step by step, or perhaps you would have to, you know, kind of like do more practices and try to get an idea of it, like see it from different perspectives. There is no one solution where I can tell you, oh, the graph is like that, okay, you can answer all the questions already. There ain't no way. That's not happens, and that's not gonna happen. Physics is a practice type of subject. The more you practice, the more exposure you gain, right, like you will do better. Right, I was telling the other class the other day, the year 4 class, don't ask me how many more papers there are to do before the exams. Ask yourself, how many papers can you do before the exams? That's a totally different question, right? If you ask me every week, oh, how many more papers are? You're just waiting for an end goal, right? But if you're asking yourself, oh my gosh, I need to whack out at least 7 papers more before the exams, yeah, that's a sign of success. Don't ask how much there is more. Ask how much you can do, how much more you can do. Okay, so that's the answer for this. Just one last thought about this one here. If I were to overlay this graph, right, this graph onto this graph, right, if I were to overlay this graph onto that graph, right, this orange line will take the initial gradient, right, it will take the initial gradient, right, and it will be like the tangent, okay, it will be like the tangent to the initial gradient of, right, it will be, this orange graph will be tangent to the initial gradient of this one here, right? Okay, so stone A starts off with G as well, right, because there's no air resistance at the start. As it keeps on falling, the drag gets more and more and more, right, then it starts to, right, the graph starts to, like, you know, steer away from that line, right, from the gradient of 10 meters per second squared line, like this. And then finally the gradient of a stone falling in air resistance, what's the gradient here? The gradient here is 0, right? No more acceleration, that's it. But the stone that's falling, right, without air resistance will continue to fall, right, with air, like, you know, with acceleration of 10 meters per second squared, right? There you go. So this is this is what I was I mean, this is one of the questions that one of the students was asking. So I'm just gonna screenshot and paste it over. Oh gosh, sorry, it's not a complete picture. Okay, I'm gonna send it to the group chat. All right, so that was I guess that was a little bit of a warm-up. What I want to do now is I want to continue with the ACS paper, right? So this is the ACS paper. So I did 1 or 2 questions. I think some of you asked me a question here and there. So you know what? I'm gonna ask you all again. In the chat here, could you just type out the questions that you need me to cover, right? I did say to do the paper by last week, and Saturday I covered all your questions. So that's why I'm holding this session now, kind of like to be fair, right? So that we can like, you know, cover more of the paper here, right? So could you all just type in the chat here like this? There's no need to private chat me. Just type it into this box here, right? Whatever it is, let me know which questions you want me to go through. Like now. Okay. Is this paper right, guys? Seth? Okay, can. Okay, can. All right. So how many marks is this? Sorry, this one is 40, right? 40 to the waist. Well, okay, depending on your like which topics you're supposed to do. Okay, let me just give you a bit of a gauge, right? Assuming you do all, right? Assuming you have to do all, right? And this is not the same for everyone, but you use a percentage. If you are getting 32 upon 40, this is the bare minimum, right? This is the bare minimum. Now, I don't chase grades. I chase understanding. So if you think that I'm a grade pusher, right, you are seriously very like mistaken about what I do, right? I chase understanding. I want you to understand the concepts. I'm not the kind like, oh, you just memorize the thing. Every time you see this question come out, you just memorize it and then you do it that way, right? I'm not the kind of that kind of people, right? I don't know what kind of people those are, but there are those people out there, right? I'm not the kind. I chase understanding, but I use this as a gauge. 32 out of 40 is a bare minimum, meaning that if you want to get A1, right, this is like you're borderline not getting the A1, right? Because this is an indication that you have good understanding, but you're quite careless, okay? So this is bare minimum, right? So the trick to physics is this: you get it, that's great. There is no way to force your understanding. It's not like you can squeeze or wiggle your way out, right? Like, I don't know, literature or like, you know, history, like, you know, you BS your way through, right? This is not it. You get it, you don't get it means you're going to lose the marks. So an indication of 32 or 40 is a big green flag to me, saying that, okay, you're ready to receive your A1, but you just have to be a bit more careful, right? The target score is always going to be 36 upon 40, right? 36. That's my target score for a blanket every other year, right? If you're getting the likes of 28 upon 40, which means 70%, okay, you are at the danger of dropping into the C zone, right? Very close to C, right? Yeah, you might be thinking, but 70%, gosh, like, you know, aren't you a bit harsh? So you get what I'm saying? This is an indication of your understanding. If your understanding at the MCQ level is 28.40, your paper 2 is cooked, right? There ain't no way for you to be able to I don't think you are the type to be able to get a higher paper 2 score than 70%, right? Your paper 2 is definitely going to pull you down really badly, right? You're going to tank your grades up to like C5, C6, right? So these are your indications, right? A 32 out of 40 is bare minimum, a 36 out of 40 is my target, right? A 28 out of 40, all right, you got to review what are your mistakes and you start patching up your knowledge gaps, right? Like I say again, physics is a very absolute thing. It's either you get it or you don't. If you don't get it, go patch it up. There ain't no way for you to wiggle out of it. There's no like, oh, I'm gonna force myself to understand this, right? No way, right? That ain't not gonna happen, right? Not in a million years, right? You wanna prove it to me? Sure, go ahead. But you know, 15 years, right, of experience, I know this shit. Okay, all right, got enough questions being posted to me now, right? Okay, for the record, that's not a lot of questions. That's a bit surprising. I thought I got you. Don't tell me that you checked the answer key already, right? So the last two things, right? The last two things I want to hear from anyone is number one, oh, I checked the answer key already, all right? That's a big red flag, all right? Checking answer key just means that you only want to care about the answers, but you don't really care about what happens, okay? All right, so that's a big red flag. Oh, I checked with my friends. Oh gosh, that's another major red flag. All right, I checked with my friends. Gosh, your friends, all right, I'm sorry to say, even the brightest one, they are really smart. But if you want someone to convey the concept to you, that's a totally different thing. Okay, or I checked with my teacher already. Again, let me remind you, your teachers are tired, right? They have to handle 40 students in a class. They have 5 to 6 classes, right? If every single one of them asks a question, their head is gonna burst, right? So what they do is they'll just tell you the bare minimum for you to understand, and then it's like that lah, like that. You don't get it, man? It's just like this, like that lah, right? So all these excuses, right? I'm recording this, I'll play it back to you again. Those are all red flags. And I can show you, right? Every single time, every single year, any other student that always tells me things like, I checked the answer key, I checked with my teacher, I checked with my friends, C. Automatic. It's always a C or worse, D. Right? It's just, you know, it's because of the way you are approaching this thing, right? There's the amount of respect that you're giving yourself for the subject, right? You know, you are not bothered to find the true answer, right? Because you just want the easiest way out. You just can't be bothered to find the concept. I understand that, right? It's just, you know, shortcuts. People love shortcuts. But let me ask you, do you want to take do you want, you know, a renovation, right, to take shortcuts? You wouldn't want that, right? Do you want someone that makes your car to take shortcuts? You also don't want that, right? So why would you take shortcuts for your understanding here? That's kind of weird, right? So, you know, so those are the things that you know, I you know, there are red flags to me. So if I see this many questions only, right? If I see this many questions only, and I see this many people online, and I don't see, right? Like I say again, it's all being recorded, so all your names are up now, right? There ain't no way, right? that you have no questions, right? But yeah, okay, I'll leave it to you. I can't chase you. You get what I'm saying? All I am is this digital image just yapping away. Blah, 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 blah. You know? Yeah. You know, I can't do anything to you. Right? Yeah. Okay. Seth, Enzo. Yeah? This question, what's up with this? What's your question here? You're not sure how to start, or you did some calculations so you got it wrong? Was it? Okay, so what kind of question is this? Nuh-uh, wrong. It is moments. Okay? How do you tell whether it's moments or not? Yeah, I mean, but where's the pivot though? Yeah, so basically this thing here, right, the bar is being balanced, okay? Right, you could take T1 to be the pivot, you can take T2 to pivot, right? So I'm showing you how this is done, right? So you know there's moments, you gotta have to choose a pivot, but before that, very important, moments, right? Okay, what's our standard procedure? What's the first thing we do for moments? We draw all the forces acting on the bar, right? This beam here, this bar. We draw all the forces acting on it. Two forces have been drawn for us already, T1, T2, right? What other forces do we need to draw? The weight, where's the weight? Down the center, is it the center between T1 and T2? Center of the bar, all right? So just be very aware of that. So center of the bar, right down the middle, that's the weight, right? That's mg of the bar. Okay, we go on this. How do you know it's right down the center? What's the clue? How do you know that it's right down the center? Good, right? Uniform, right? It's a uniform bar, so it tells us that, right, that the mg is right in the middle here like this. Okay, good. So this is the procedure, right? So moments, draw all forces. Right, draw all forces. Right, number two, give me a pivot. Where's the pivot? Which pivot do you want? You want T1 to be a pivot? Okay, so we put T1 as a pivot. So if T1 is a pivot, then we don't consider moments of T1. You get it? So now this is the pivot. So what we do now is we look at the other two forces, right? The other two forces here and here, right? mg, pivot is here, right? Pivot is here, mg is here. What kind of moments is this? Seth? This is clockwise moments. How about T2? What kind of moments is that? So are they balanced? Why? Why are they balanced? How do you know it's balanced? How do you know they're balanced? It's held in a horizontal position. It's not rotating. The fact that it's not rotating means that it's balanced. if they are not balanced, let's say for example, you cut the string here, Seth. You cut the string here. Right? Let's say you cut the string here. What will happen to this bar? It will swing clockwise, right? It will rotate clockwise. You get it, Seth? Yeah? Okay. So, but it's not, right? The string is there. It's holding it up. So the moments are balanced. So mg times the distance of mg to the pivot. Right? Do you see the distance here? What's that distance? That's super important. What's that distance? 0.5, good. 0.5 times 0.5 meters. Okay? Why is that? Because it's a 1 meter long. Okay? And it's balanced by the other moments, which is T2 times Seth, yo. What's the distance here? (0.8). The pivot is here. Always multiply the distance to the pivot, to the pivot, to the pivot. You want to go read out what is the definition of moments again? One more time. Moments is force multiplied by perpendicular distance from line of action to pivot, right? To the pivot. Why do you take 0.3? 0.3 is to the middle here, to the mg. That's not the pivot. You chose the pivot to be here. I asked you which pivot you want. You told me T1. So we take this as a pivot. You get what I'm saying? So mg to the pivot is 0.5. T2 to the pivot is 0.8. Like the distance is literally written here for you to see. Right? Down here. Okay. So that's 0.8. Okay. Can you find T2? Do you have mg, bro? How much is that? How much is mg? 40. Good. 40. Right. Find T2. Come on. Do it. So actually, there's only one answer. Like, you know, look at that. Look at them being so nice. Guys, what? They're being very nice. Like, you find T2, that's the answer already. Like, there's nothing else. What do you get for this, man? I ain't got a calculator. Punch it in for me, please. What's it? 25 newtons. 25 newtons. Okay, so 25 newtons, that's the answer there. I mean, there's only one here. Right, you get what I'm saying? Okay, hang on. What if it's a paper 2, man? What if it's a paper 2 question? How do you find T1? What do you do? Pivot T2, tell me. Pivot T2. This is T1 pivot, huh? Right, and then I do T2 pivot. Okay, go ahead. Tell me T2 pivot. Which is which one? Okay, mg times. Good. 0.3. And this is equals to, which is good. All right. So you can do this and you can find T1. Okay. But hang on, stop. Right. I've done at least one or two of these before. This is your double pivot kind of questions, right? Double pivot kind of questions. Remember this here. All right. So if you have already done it once, here like this, you've done it one time already, you technically don't have to do this, because what I need you to also remember is force equilibrium, right? You already found T2. T2 is what? 25 newtons, right? And you say that mg was 40 newtons, right? So the other thing that's in equilibrium is also the forces. All the downwards forces balances the upwards forces. Do you see that? Right? So 40, which is pointing down, must be balanced by T2, which is pointing up, and T1 that's also pointing up. So it has to be 15 newtons. You get it? You see? So you know, we can do this method, right? We can do this method, or we can do the downwards and upwards. But we must at least do one of these. We must at least choose one as a pivot, and then after that we decide Whether you want to do that, you want to do this also fine. That's also okay. I'm not saying that you shouldn't, right? If you want to be doubly sure, you do the upwards downwards method and then you do this method, that's fine. But you have to take the initiative to do the method. Don't sit there and then start wondering, should I do this method? Right? Just do it. Just get on with it. If you do something, you don't get one of the options here, check your working, check your numbers. Okay? Right, so that's 13. Hang on. Question 3, Gordon. Is that right? Gordon? Yeah? Okay, sorry, I'm trying to charge my phone. What's question 3? What's question 3? Question 3. This one here? Okay, cool. All right, I'll go through it now with you. All right, so, hang on. So, the object is moving in a circle. Is it clockwise circle or anti-clockwise circle? Is it clockwise circle or anti-clockwise circle, dude? Really? How do you know? Yeah, so what you say clockwise? So the answer is you don't know lah. Gordon? Yeah, so which means that it could be moving clockwise or anti-clockwise. You get it? Like there ain't no way for us to tell whether is it clockwise or anti-clockwise, right? So you choose one. Where do you want it to be going? You want it to be going clockwise? Okay, sure. Going clockwise, huh? All right. So going clockwise, I'm gonna ask you this at point A and point B. Let's say point A. Can you draw an arrow to show the velocity at point A? How would you draw it? I want you to show the velocity at point A. So tangent to the circle. Okay, tangent to the circle pointing upwards, right? Like this? Okay, right. So that's the velocity. That's the velocity. How much is it? Okay, 2 meters per second. 2 meters per second. Okay, 2 meters per second. So that's the velocity. How about at point B? Where's the velocity pointing? Downwards. How much is it? Okay, I might ask you this, okay? What's the change in speed? What's the change in speed from A to B? Right? Yeah, 0, good. Why 0 though? Cause speed direction don't matter. Right? Speed is just the magnitude. At A or 2, at B or 2, so the change is just 0 lah. Okay? Alright. But how about the change in velocity? Change in velocity. Right? So direction matters. So which means that from A, right, which is pointing upwards at 2 meters per second, 2 meters per second, by the time it went to B, it transitioned to downwards at 2 meters per second. So in terms of like you know, in terms of like arrow, like you know, arrow wise, right? Okay, would you agree that this arrow got shrunk to 0 and then it got extended to 2 downwards? Yeah, so the total change for that will be 4. Yeah, okay, hang on. There's a mathematical way of doing this. Of course, like math, right? Can I just see an equation to get the thing right? But you know, without me describing this thing, right, looking at the math wouldn't really help. So what you're doing is basically 2 minus negative 2. You get what I'm saying? Like 2, like, you know, because it's velocity, right? If one is pointing up, then the other one pointing down, then we take one of them as the negative sign, right? Because it's pointing downwards, right? It's the wrong direction in that sense. Right, you get it? Hey, where's the mouse doing that? Okay, Yeah. So you understand this? Yeah. So 2 minus minus 2, you get 4. Or you could have minus 2 minus 2. Right? Let's say you take the minus 2 direction and then you minus away the initial direction 2, you end up with 4 again. Right? Minus 2 minus 2 is still 4. Right? This is 4, this is minus 4, but the magnitude is still 4. Right? So C is your answer here. We're good? Alright, awesome. Okay, let's look at 19, Seth. Come, your turn again. 19. Ooh, this is the tough one. Okay, let's see. Oh, but I thought I went through this briefly, but it's okay, I'll do it again. So it's saying that at the top, the speed of the ball is 3 meters per second. Right? 3 meters per second. And what they're asking for, they want you to find the speed at the lowest point, right? So they want you to find out what's the speed, right? When the ball has gone down like this at the lowest point here, this will be like the speed, right? I don't know what's the speed. They're trying to find the speed. So again, I think the big question is this, because I know you probably weren't around for the earlier chapters. I think this might be an early chapter. Which chapter is this? Yeah, it is, right? So work, energy, power, right? Okay. So what does the ball gain as it's going down? Okay, like again, okay, like there's energy is transferred to its kinetic store, you know? Okay. Ugh. Right? Energy is transferred to its kinetic store. That means its kinetic store gets fuller, okay? Oh gosh. It gains kinetic energy. Okay? But from what? Okay, good. So did you try working here? You did, but you got it wrong. Okay, all right, right. Let me guess what you might have done. Did you do this? mgh equals to half m v minus 3 squared. Do you do that? Okay, hang on. So you went to do mgh equals to half mv squared, then you took the v and then plus 3, is it? Did you do something like that? Which one? This one? Like that? Okay. Okay, red flag. Red flag. Never ever do this, okay? Never ever do this. I'll point out to you what's the proper method. I won't try to explain why this is wrong, but I think it's more important to know what is the correct way to doing it. Okay? Alright. Right. But I'll fix why is it wrong later on. Maybe this Saturday I'll talk about it, but definitely now, because we try to do more questions, right? I need you to know how to do the correct method. Okay. There's initial KE. Right? Do you see that? KE initial. KE initial. Then there's final KE. Final KE, yeah? Right. We know that final KE is more, right? Yeah? So KE final is equals to the initial KE plus MGH. Do you guys see that? Okay, so half mv squared equals to half m3 squared plus mg2r. Right? Do you get why is it like that? Why 2r? Yeah, because it's a height, right? Right. So if you didn't realize what's happening here is that if you rearrange it, it kind of looks like this. It becomes half mv squared minus half m3 squared. Okay? So you got to remember, I don't know whether you attended this before with me, but you got to remember, change the KE is always half mv squared minus half mu squared. Right? It's not v minus u bracket squared. It's v squared minus u squared. From a math perspective, you understand that's different, right? But you always have to do it this way. Okay, good. Right, so I'll leave that to you, right? I don't know what the final answer is, but you can punch it in and you should be able to get it. Sorry, Sarah, I got 18, sorry, 18. Oh, I just saw your message at the bottom there. Okay, sorry, did somebody text me? Wait, did somebody text me? I can't, where's my phone? Did somebody text me for a question? I don't know why my phone, I can't unlock it. Hello? Sorry, what question do you need? Sorry, my phone is like I think it's hanging because, sorry, which one? 33. Okay, hang on, we'll do it later, but thank you. All right. Okay, so 18, right? 18. Many times done already. Okay, many times. All right. You know, at some point it becomes a little bit annoying. Right? So just please make sure you remember this. Right? I don't know how else to tell you. Right? Because you know, I mean, I get it, right? Every other year, right? I will be explaining this like 10 times, 20 times, right? You know, exam comes, you know, this thing still gets wrong. So try not to make that a habit, right? Because then you'll be stuck at this thing. Like, you know, the time that I spend like teaching you stuff, it'll be like, oh, you know, today 9:30 p.m. on 22nd September, I'm doing this question. Previously, I was doing the same type of question. Previously, I was doing the same type of question. So, you know, it becomes accumulative, right? So if you don't get it still, then come next year, right? We start learning electricity. We start learning electromagnetism, right? This is still going to be a problem for you, which means that somewhere down the road, next year, more time is spent on this again, one more time, right? There's, you know, I mean, if you want to conjure another way of how to do these questions, right, by all means go ahead. But I believe in using that same standard method I always use so that it doesn't confuse you, so that you always get it, right? You always do it the same way. Which is why there's a danger in checking answer key, asking friend and asking teacher. Because you check answer key, they give you a different method. You check friend, they give you their method, right? You check teacher will tell just kind of like, you understand this, right? Please go away. That sort of thing, okay? But at some point, right, if this doesn't click, then I'll just send you all the recordings of all the times that we've done this many times over, and you're going to watch it all over again like 2 to 3 times more, right? So if I've done 10 times of these kind of questions, you watch 2 to 3 times more, you're watching it about 20 to 30 times, right? Until you get it, okay? So there is a standard procedure, right? Kind of like how when we wake up, we pick up the toothbrush, we put the toothpaste on, and then we brush our teeth, right? It's the same standard procedure. Like, you don't have to think, right? It's the same standard procedure, like, you know, yeah. So I'm prescribing to you a sort of like a habit. You see this question, manometer, liquid, same level, same pressure. Right, same liquid, same level, same pressure. What that means is that for the same body of liquid, right, this one here, which is water, at any same level, they have the same pressure. And we usually take this level and this level here. Right, so we have one level here and we have another level there, right? At these two, right, along these dotted lines, right, along this dotted line, they have the same pressure. They have the same pressure, right? Okay, now, same liquid. What do I mean by same liquid? Same body of liquid. Look at this water body of liquid, continuous body, right? This whole body here, right, at the same level, they have the same pressure. Of course, oh, can I compare here and here? Look at the two red crosses. Can I compare there and there? No, ain't no way. Those two pressures are completely different, right? Why? Because they're not the same liquid. This is water over here. That's kerosene over there. There ain't no way, right? So we're taking the border of the kerosene and water, the top level of the water, and we're taking the water over here, same liquid, same level, same pressure, right? Okay. Right. Then we ask ourselves, what's above that point? Like, what's causing the pressure above this point? Okay. So above the point on the left side, let's say I call this A and call this B, okay? Right? Above the point on the left-hand side, what's causing pressure? This liquid is causing pressure and the atmosphere. Okay? So liquid, water, and atmosphere, ATM. So pressure A, right, is equals to pressure B at that levels, right, at that level. Atmospheric pressure of A is, sorry, PA is ATM, atmospheric pressure, plus H rho G, right, H rho G, right. These are just letters, right. These are not like math symbols like differentiation or integration. These are just P ATM plus H rho G, right. That's rho, right. Some people like to call it P, but it's confusing after a while because then it will be like P equals HPZ. Then you think that this P here is pressure, is H rho G. This H rho G is for the water. It's like here, this one here, we're referring. So I'm writing whatever this one is, right, is this one here, okay? So that's water, but never mind, I'll equate it to the other side. So the other side is B, I'll use a different color, right? It will be the H rho G of kerosene and atmospheric pressure. So on the other side will be, right, atmospheric pressure and H rho G, right, of kerosene. So this one is kerosene, right, kerosene. This one is water, right. So it just so happens that both PATMs cancel off, right. So you got H rho G of water equals to the H rho G of kerosene, like these two levels here, right. They exert the same amount of pressure, right. So water, 10 cm of water is equivalent to HCM of kerosene. So now we start filling in the numbers. Right, so I use the next row. So this is 10 cm is 0.1 meters times density is 1000 because they gave me 1000, right? That's the density of water up there, right? So I use 1000. This is water, right? And times G, which will cancel off. So I mean, you know what? Actually, it cancels off. So I don't need to bother about G anymore. So it's the H rho of water equals H rho of kerosene, right? So I don't have to. Now this is just like, you know, we are just working it out, right? So H rho equals H rho. So down here, this is H times 810. Okay, all right. So there you go. Then after that, you make H the subject, right? I don't know what's the working, but is this okay now? Yeah, you got this right? Okay? All right. Can you tell me where you went wrong? No, you're right. You're right. It's two different liquids, yes. But you see this level here? Yeah. So this is like the top of the water. This is the boundary of the water. We can take that level. Right? We can take that level. Actually, that's not an issue. That's not an issue. I was just trying to show you the proper way of doing it. Like H should be in meters. So I you know, I'm supposed to use, like, I can technically use 10 cm here. In fact, if I use 10 cm here, then my H will be given to me in cm, right? Which will be one of the answers here. What I did was converted it to meters, right? You see, this kind of question is a ratio question. If it's a ratio, right, the units are the same on both sides, right? So if you use cm here, it will end up be cm there. If I use meters here, it will end up with meters on the other side. So that's not the issue. I think the issue here is you got to see that, yeah, I know, I get it. There's two different liquids. So, you know, it's like, oh, why is it not same liquid, right? So for the parts that are the same liquid, they at the same level, they have the same pressure. That's what this statement means, okay? Yes, if, like I say, I was just trying to show you, right? You compare these two parts here, you see these 2 points here, this red point here, and that red point there, right? You see those two there, right? Are they the same liquid? They are not the same liquid. So we can't compare the two pressures here. We can't say that these two red crosses have the same pressure. You get that? So that's that, yeah. But we choose this level. We choose this one at the bottom here, the purple ones, right? We choose the ones at the bottom here, this one's here, right? So we choose this one here, right? Where my finger is like down here, right? We choose these 2 points because they are the same. They're water, and on this side, that's the top surface of the water. So still the same liquid, and they are at the same level, so they have the same pressure. then we see what's above these 2 points. So on one side is 10 cm of water, on the other side is HCM of kerosene. Okay, right? So there you go. Right. I got a request to backtrack to 5. Let's look at 5. Okay. All right. What's this thing here? Sorry. What's this about? Okay. So for this particular question, this is I mean, it's not easy, but if we do this 2 times, 3 times over later on, right? I mean, it will come to a point whereby you realize that it's always going to be like the same way we do this, right? So for starters, I want you to draw the scenario. So if you haven't drawn already, I want you to draw, right? This cliff. You draw a cliff, right? You draw a cliff, and then you draw a person standing here like that, okay, standing there, and then he's throwing the stone. Throw the stone, and where's the stone going? The stone is going up, right? The stone went upwards, right? So there's a stone. We throw the stone, right? Throws upwards like that. Okay. What's the initial speed of the stone? What's the initial speed of the stone? 5. Okay. So at some point it's going to go up. It will not continue going up forever. It will come back down. Right? You understand this? Right? It will come back down and then it will hit the ground. Right? Which is at the bottom of the cliff. So this kind of question where they say cliff, right? It's always this kind of scenario, right? You throw it up, it comes back down. Okay. So they're asking for the height of the cliff, which unfortunately I think this is a bit confusing now because, like, you know, the person here like this, right? Hi Sonia, why are you annotating on? No, that's fine. Don't worry about it. It's just quite funny. That suddenly there's like a few dots over there. So I'm just gonna cut out the guy, right? And imagine that this guy is like, you know, he's really small, right? And he's throwing the stone up, right? He throws the stone up like that. Okay. Our job is to find what? Like, what are we supposed to find in this picture here? That means here, right? Are we trying to find the the maximum height where the ball went up to? No, right? Just here, right? Okay, good, right? So yeah. So what you need to do, right? What I would want you to do is I want you to map out, right? Exactly, like, you know, the positions of this thing in the graph. Like, you know, where is it on the graph? Okay. So the starting point is at the starting point here, right? Is at the starting point here. So that's where the starting point is. That's where the starting point is. Okay. So we have, I'm going to call this A, point A. This is point A. Right? Okay. So as it goes up, what's the speed up there? What's the speed up here? Like this? 0, right? Okay. So this is the part where it gets a bit confusing for some students. The stone is going up, but the graph is being drawn down. What? Are you like kind of like confused by this? So why is it that the object is going up, but the graph is going down? Because this is not a displacement time graph. This is not a distance graph. This is a velocity graph. Like, it literally maps the velocity of this stone every point along the way. Right? You get that, right? Okay. So that's why at point B, that's like the highest point here. This is point B. Right? That's point B there. Then this stone is going to start falling, fall. It's going to come back to its original position where it was at, right? Which is like point C here, like this. So now this is the point, like, you know, like, we need to figure out where point C is on this graph. Like, where is this point C on the graph here? Okay. So you can use the distance, you can use the area. So you see this area here, you see the green area here, right? This area here. That's the distance where? That's the distance from A to B. That's distance A going upwards to B, right? That's this distance here. You see that distance over here? Okay, how about from B to C? From B to C, what's the distance? Is it the same distance? So which means that on the graph, if you can find out, hey, isn't that the same exact area, copy of area over that side from here to here? And how about from C down to D, right? D is at the bottom. D will be at the bottom here like this. You got that? So from C to D, the area would be here. That would be the height of the cliff. However, we are missing this value here. Do you see that? You're missing this corner here. This value where I'm pointing at. You can see me, right? Yeah, I'm pointing here. Yeah, we don't have this value here. Right? Yeah, so can you make a guess how much that is? Because that's your last thing you need to do to be able to find the area here. -5. Right? -5. Alright, there you go. Can you find the area here now? Do you understand the area of trapezium? Alright, then you can find the distance over there. Okay, so that's for 5. Let's go on to, I think, Sarah 18, 19, 18, 19, 5. Okay, so more or less cover everything. I think Nicola is asking for 33, is it? 33? Okay, why is steam at 100 degrees Celsius more harmful than water at the same temperature when it comes to contact with our skin? Hang on, let me just double check. I mean, if we have enough time, Seth. You got questions from it? Seth? Okay, hang on. Let me see what I can do. Gosh. Yes. Okay, so in the Telegram, I forwarded a statement the other day down here, one from one of my year 4s, right, doing the same question, right, similar question, right. It says, when steam condenses to, well, so this is my answer, right. So it says, why is steam at 100 degrees more harmful than water at same temperature when it comes to contact with our skin, right? So based on that Telegram, right, the statement here, like I typed it out because it was a paper 2 question. It could be a paper 2 question for you, right, for all of you, right? When steam condenses in the water at 100 degrees Celsius on skin, it releases latent heat, right, to the skin at the boiling point. This causes a lot more thermal energy to be transferred to the skin than just boiling water alone, hence steam causes more injury. That's the answer. So if you look at this, right, C, steam condenses to water, transferring a large amount of latent heat to the skin. That's the answer there. You got this? Okay, cool. What were you confused by? No, that's fine. Yeah, so now we know it's because it's latent heat, right? just to give you guys an idea, right? So kind of like I always like to give you the answer, but also I'll follow up with a short explanation, right? The explanation is where the important stuff is, right? So guys, okay, so let's say you have 1 kg of water, right? 1 kg of water, right? And the values I'm going to quote you are actual values, right? So specific capacity of water is 4,200 joules per kg Kelvin, right? Joules per kg Kelvin. Latent heat of vaporization of water, right? Latent heat of vaporization of water is, that means this is the amount of heat that you need to convert water into steam, but at the boiling point, okay? 2250000 joules per kg, okay, per kg. What this means is that if you're trying to heat water up, right, if you want to heat water up from 25 degrees Celsius to 100 degrees Celsius, for example, right, 100 degrees Celsius, like how much energy do you need, right? So heating, right, this is heating. Heating is equal to 75 degrees, 100 minus 25 times 4200, right? That's the amount of heat you need to raise from 25 to 100, okay? Looks like I have to pull out, so since I'm the one who's commanding this, so I have to pull this one out now. Okay, so 75 times 4,200, right? 315,000 joules, 315,000 joules to heat from, right? To heat from, 25 degrees Celsius to 100, right? We need this amount of energy. Okay, so this is the amount of energy that boiling water has to lose before it cools down to 25. But how about steam? So if you want to convert this 1 kg of water into steam, right, how much energy do we need? Since we have 1 kg of water, we need 2.25 million joules. 2.25 million joules, right, of heat to convert water into steam, right, 100 degrees Celsius. So when steam condenses, steam is going to release that heat to condense back into water. So for 1 kg of steam is gonna release 2.25 million joules, right, of heat just to condense back to water. So I mean, I think numbers wise, I'm guessing you guys can tell that 2.25 million is a lot more than 315,000. But it's not a very fair one-to-one comparison, right? Because this is raising the temperature from 25 to 100, and then this one is converting the water into steam, right? It's not very fair. But the idea here is that latent heat is a lot of heat, right? Latent heat is big, right? So therefore, that's the idea. I'm trying to drill that image into you, thinking that yeah, steam condenses the water, transferring a large amount of latent heat to the skin. Right, that's one number 33. We got a request for 40, Garen 40. Is that you? Okay, this one here. Sound. Do you do sound? Are you doing general waves? You are, right? Okay, good. All right. So, like, for those who are doing waves, let me just do this one very quickly for him. So, higher than what? Yeah, like I said, but I just mentioned, right, it's not a very fair comparison. Yeah, it's not fair. It's not like a one-to-one. It's not like, I mean, we are sort of like comparing apples to like guavas. Oh yeah. I mean, you saw my text, right, on the telly. Yeah, this one here, right? So basically, like Ben, he was asking like, he was asking this same question, but it was in the paper too. So he was asking, how do I write the answer? This is how you write the answer. Yeah, that's right. Yeah, I mean, what the temperature of steam and water is actually the same. It's 100 degrees Celsius. They're both same temperature. Yeah. So we like, you know, yeah. And therefore the only difference is really just the latent heat. Yeah. Hang on. Okay. What? Well, 40. Yeah, 40. Sorry, Garen. Yes, you. Oh, hey, Garen. Right. Slower, shorter, shallow water frequency stays the same. So refraction, frequency stays the same. Yeah. So straight away, this one, right? 2 second question, 50 hertz. Go in the water, still 50 hertz. Yeah. Okay, for those who do refraction, okay, just a quick one, just a quick one. I don't remember when I did this with them. So those who are not doing waves, right, just kind of like just block your ears for a bit, right? So those who are doing waves, right? So yeah. Garen. Okay, you do light, right? Do you do light? Oh, okay. But you do waves lah. Okay, so I mean, and for those who are also doing light, like I guess for the SGI guys, Enzo, Aiden, and Gordon, right? I think I want you to pay attention to this one, because you do light and then you do general waves as well. This is kind of weird though. SGI has so many topics for year threes. Okay, um, right. I mean, for those who are doing general waves, understand this, right? Like you should understand that light bends towards the normal, right? Light bends towards the normal, right? Because it, you know, once light goes into glass, it slows down, so it bends towards the normal, right? Right. So this one here is light slows down, bend towards normal. Okay, right? But Garen, just to make sure, do you understand? Uh, no, hang on. Do you understand that if it's sound, let's say I have a sound wave. Hang on, let me just change the color of this thing here. Right, so this, let's say this is a sound wave. Sound wave enter glass. What happens to that sound wave? It bends away. Okay, so in general waves, they actually do teach a little bit of refraction. So this is just me making sure that you have the idea of refraction correct, in case it comes out. Can And then for the SGI guys, right, please take note of this as well, right? So kind of like you need to know both. Light will slow down, but sound speeds up in solids, right? Sound travels faster in solids. We okay with this? Yeah. All right. So MCQ done, right? I don't want to hold it too long, too late, right? I think you guys are Sec 3, you guys are, you know, still need to sleep early a bit. So let me just, I mean, I still got this Saturday to go through. So let me just go through. Right, so let me just go through some questions. I don't know. Nicolette, I think I saw your message. Sorry. You're requesting for A1, A5, B2. Is that right? Yeah. Seth, how are you? What are you requesting for? A1 also. Okay, well, that's fine. Okay, A1. Let's look at A1 then. Right. Okay, A1. So, you know, looks convoluted. It's like, whoa, what's going on, right? You've got this weird thing, and then that thing, and then this thing, and then that thing. So you gotta understand, I'm here, right? This is our lesson. I can break it down for you, right? Exam time, I'm not gonna be there. I'm not gonna tell you like, hey, you know, this is a retort stand. You have to kind of like break it down for you, right? Kind of like figure out where the action is happening, right? So the action is happening around here, right? There seems to be a weight pulling something down, they did mention, oh, there's a tension here, right? It's not a straight line, it's a diagonal line. And then there's a force here like this. Oh, but there's a spring balance there, right? So it makes me feel like, oh, I technically can measure the force using the spring balance. So I can probably find a weight. I can probably find out how much force it is at the spring balance. But, you know, for the tension here, I don't think so. I think it's something that probably we might not know, okay? Right, so we probably might not know. So we need to look at this thing here. It says, taking moments about, ooh, okay. I was thinking, okay, I've never seen the paper before, guys, right? This is the first time. I was thinking they may ask you to draw a vector diagram. I was half thinking, you know, draw a vector diagram, but no, they're asking you to take moments, right? Take moments. So let's do this. Okay, taking a moment about point A literally means what? Make A the pivot. So we go back here, right? Go back to this point here. Oh, we're gonna make A the pivot. Okay, A the pivot. So we're gonna make A the pivot. So I'm gonna draw the pivot there. Right. I follow instructions. That's what they want me to do. Don't ask like, oh, how about could the pivot be anywhere else? Sure, that's another question. They want me to take A as a pivot. I take A as a pivot, right? So we have a pivot, and they want us to use moments to find F. They want us to use moments to find F, right? Taking moments about A, find F. Okay, every force has its moments unless it's passing through the pivot. So look at this guy. Look at the tension here. The tension here, like this. It's passing through the pivot. You know what? We're gonna ignore the tension for now, right? Because the tension passes through the pivot, right? So we can ignore it. So what we need to do is we need to find the moments of F, right, with regards to the pivot here, and we need to find the moments of W with regards to the pivot here. Same pivot. Okay, same pivot. Now you might be thinking, oh gosh, this looks really complicated at this time, right? You know, there's so many things going on, right? Filter all the unnecessary things out. What do you need to care about? Pivot is here, right? Pivot is right here. Unknown force is there. W is here. These are the things that gives you the moments. Don't have to consider the T. T is passing through the pivot, right? And I get it. Some students will be like, oh, so do you mean that every time the force passes through the pivot, you don't have to care about it? Yes. Right? So we don't care. It's not that it's gone. It's just, if you choose this pivot, we can ignore this force for now. Right? So we got a force, we got a W. All right, let's filter it out. Let's just draw pivot, F, and W. Right? Let's draw the pivot, F, and W. Okay? Let's make it like, you know, really, really simplified. I have a pivot here. This is my pivot, pivot A. The force was somewhere around down here at the bottom. Okay, the F here, like this, there was an F there, right? And then there's a W there, like this. Okay, right, W. And then, you know, like that. Okay? I'll flip back and forth for some numbers. I think I need to use W. I need to find out what's W. So what is W? W is 15 newtons. Is that right, Nicolette? 15 newtons, W? Okay, so W is 15 newtons. But I have to do this moments style, right? I have to do this moment style. So let's not forget that there's a pivot, right? It's like, what's going on? Like nothing's connected. I got two arrows here. That's fine, right? There's actually nothing more than this, right? So what we need to do is we need to figure out, right, what kind of moments. So are the moments balanced? I think first question, is the moments balanced? Nicolette, are the moments balanced? How do you know? Yeah, it's not moving. It's kind of like held there, right? No moment, no. That means all the clockwise and anti-clockwise moments are balanced. Okay, right? So you see that the standard procedure is the same, right? So this force here, right? The pivot is here. The force is here. Ooh. What kind of moments is this? What kind of force? What kind of moments does the force give? That's clockwise. Okay. Then the weight here, but the pivot is there. So clockwise to anti-clockwise. Alright, clockwise to anti-clockwise. So what we need to do is we need to find out force times, this is the part that's a bit tricky. So force times what distance? How do I find the distance? So it's always line of action to the pivot. So the line of action of the force is this dotted line here. Right, that's the line of action of the force. Okay. So the distance I need will be this distance here. Right? Okay. Again, one more time. I give you a line. Right? I give you a line. I give you a point. What's the shortest distance from the line to the point? You drop a perpendicular. That's what you're doing here. You're dropping a perpendicular. So that's the distance that we need. So this is like the distance for F, right? So I write dF first, right? This is the distance for F, right? So force times distance for F is equals to, right? Force times distance for F is equals to the weight, right? But where's the line of action? The line of action is vertical, right? So it's gonna go like this up, right? Vertical and down, like that, okay? So now I use another color like this, right? And then you can basically, you need this distance here, right? This will be the dw, right? That will be the distance for the weight that you need. Line of action to the pivot. Line of action, perpendicular distance, line of action to the pivot here, right? So that will be W times dW. So now what we need to do is we need to go back to the question and then go and find out all the distances that we need, right? Because I believe distances are given, right? We need to find force. So we go back to this question, right? Oh man, what's the distance we need? So this is dF, right? This thing here from here to here, this is dF, right? How much is that? No need. Look bigger picture, look at the whole setup. $40, good, right? So 75 minus 35, right? This thing here is 40, right? So we'll take it as 40, right? So F times 40 cm equals to W, which is 15 newtons, right? 15 newtons times that distance there, that distance there. So you know, kind of worried as well. Do we need some special thing to find that distance? Oh yeah, that looks like a very strong probability. So we kind of like we will need this distance. This one will need the trigo. So it's not a normal kind of question to ask, right? Because asking students to use trigo to find the distance is hard. Did they give you an angle in the question somewhere? No, they didn't give the angle. Oh shit, yeah, that's right. I forgot we already found this one already. I forgot this one's 40 already. Okay, right, got you, right, 40. You know what? 40, 50 is gotta be 30. Yeah, right, Pythagoras number, right, the magic triangle. So that's 30, good, that's 30, right? So this is 40, right? So 15 times 30. And there you go, that's F, right? You'll be able to find F, that's it. Okay, no, so here's the thing, right? It's sometimes it's so frustrating because, right, you look at these 3 marks, okay, so if let's say you take pivot A, ACW equals to CW, F times 40 equals to 15 times 30, and then you find F. Then that's your answer. Like what? That's hardly like, it's like what? Okay, so this sort of thing will happen. So just to understand that sometimes marks are compounded, right? Which means that you need to understand the distances, you need to understand its balance, right? And then they can award you the full 3 marks. So it's a thing, right? It's a thing. Okay, right. Which one? This one? Okay, so let me clean this up again, right? So you're asking for the weight, is it? Okay, good. So the idea here is they did say they want point A to be pivot. So we're going to take this point A as a pivot, right? Point A as a pivot. You get this? And whenever you're doing moments, right? Moments, one more time, from just now. Moments is what? Force times perpendicular distance from line of action to pivot. Okay? So the weight is pointing down here. Do you see me drawing the arrow here? The weight. Yeah. So it's like, it's very unnerving because it, like, you know, it's like, but the arrow is here, right? The arrow is here. Why is 50 not the distance, right? So some people will be like, I want to measure this distance from here, this point to this point. I want this distance. Like, you know, why can't I multiply it by 50? So you have to remember, that's why definitions are definitely very important. All right. It must be from the line of action. Nobody ever said that it's from the force to pivot. It's from the line of action. So you need to extend the line of action. So you need to extend this one. Right, do you see that? I extended the line of action. Sonia? Yeah, I extended the line of action. You see that, right? And then the distance is from the line of action to the pivot. This distance here, which is this distance here. Okay, so sometimes, yes, a bit of geometry, a bit of Pythagoras, right? It's a thing. Like I can't tell you that, oh, I hope it will never come out for your exams, right? I can't tell you that. This is more like it definitely will come out for your exams, even if you're talking about like the actual O-level exams, right? What we are doing here is we are just trying to prepare you for your school exams. And I swear to you, I'm like, this is legit. This is not beyond any of the express students here, right? This is kind of like it's still within scope, right? It's just that maybe their diagram is a bit more complicated. Maybe sometimes it's just badly drawn. So, you know, it gets a bit complicated, right? But no matter what, these are all still within scope. If it's something that is really not within scope, I will let you know. I will tell you that, oh, you know what, this is a bit too advanced for you. You know that I've been saying that. So if I don't say it, means that these are all within scope. Okay? Yeah, so that's why that's the tough part is trying to find that distance, the 30 cm there. Do we need to do this one, Seth? Oh, you got this. Damn. Okay. Oh, this is another Cliff question, huh? Okay. A2. Wait, hold on. What was the request? Who else is requesting? A5B2, huh? A5B2. Okay, let me tell you what. Right, it is a bit late. Does anybody have any last minute questions? Sorry, Nicolette, are you okay if we continue this on Saturday? Right, so I think the next one you wanted is A5. Let me just scan through A5 very quickly. Guys, these are, okay, I just spotted something. This question here is not for express. So this one here, not for the express, right? The IPs, you need to do this because as far as I know Garrett needs this. I know Kira would need this as well. Zeph will need this as well. I think Amber might need this. I'm not sure. I think kinetic particle theory. I think for RGS is still like that. Yeah. So this has been officially out of syllabus for Express, right? Like this particular question. Sorry, did I mean? Okay. Right. Not the whole question, just this part. Okay. right? This is slightly not for express, okay, not for express. But I will explain a little bit of this on Saturday, right? I'll come back to this on Saturday. And then, oh, is that what you were asking for? A5? A5 part B. Oh, you're asking for this. Okay. I'll tell you what, I'll go through this on Saturday because right now I think if I go into this, it's gonna take another 10 to 20 minutes. So I think I better just leave this for Saturday already. Okay. Meanwhile, right, I'm gonna call it a day. But meanwhile, if you have questions from your school papers, please continue to post, right, in the Telegram, right? I'm still gonna go through this paper. Sorry, what? B1, let me check B1. So he's got a question for B1. B1. Okay, B1. Yes, B1 is, but it's too convoluted. This one is too convoluted. So I'll explain what's going on for this one. For the ones who are IP, this one is possible, but this one for Express is a bit too convoluted. But this one is still within the fundamentals, right? We still can. It's just that this is a more complicated scenario. Okay, I'll continue doing this paper on the on Saturday. I don't think I will be able to go through another paper on Saturday, so possibly I'll only have enough time for this. But for those who already finished doing this paper, I should be setting you another paper, right? Did I set another paper already? Guys? Did I already set another paper? Oh yeah, I did. Okay. So after the ACSI paper, we're gonna do the GMSS paper. Right? Yeah. It's inside the shared drive. Okay. Right. So it's a year 4 paper, but just do the topics that you're tested on, right? So that's the deal with me, right? I think some of you already more than half of the topics, so you can start doing the year 4 papers already. It's just that the last few questions you can just skip because the electricity and nuclear questions are not within your syllabus yet. Okay, thanks very much, guys. It's kind of late, 10:10. All right. I think it's time for you to go to bed or maybe do other things. I don't know, but yeah. Right. Bye bye. Thank you. Bye bye. Thank you. 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 Bye, Dun.